Hello everyone. So let us start our discussion on individual types of chain growth polymerization. We will start with free radical polymerization. Now here we have to understand one important point is that free radical polymerization is associated mostly with the vinylic polymers. Okay, that means alkene-based polymers. Okay, and most of the commercial polymers that are available are basically alkene-based polymers. Okay, so basically we call them as vinyl polymers, and therefore the polymerization involved with the vinyl moiety is called as vinyl polymerization. And as we know, it's an addition polymerization, or more specifically, it's a chain growth polymerization. Okay, so all these different types of polymers you will be dealing in module 5 and 6. But it's always better to know about these terms. So please, I would request of all of you to please go through these terminology and try to draw these structures, because that would give you a handy information about the structural aspects of each of the monomer connected with the corresponding polymers. Moving further, uh, we have, as we know, that many of you know about this particular thing, that in the polymerization, free radical polymerization, there is always uh, initiation phase where your monomer is kind of activated using a free radical. And then you have a propagation phase where that activated monomer reacts with the other monomers to form proper chains, and then ultimately the chain is terminated. And this particular three-step protocol, you are also pretty aware because you have often studied them in your lower classes. So you are pretty aware of these three stages in a free radical polymerization. But we are going to look into more discrete and more comprehensive points connected with each of these process. Okay, so coming to the chain initiation, we can have the monomer or the chain initiation happening via a free radical pathway, or a cationic pathway, or a anionic pathway. Okay, so that is what we are going to study, three different ways of chain initiation. Okay, and right now we will first concentrate on the free radical polymerization. And we know the free radicals are basically coming from free radical initiators, and some of them you have already learned in the previous, possibly in your schools or in your um, lower semesters. You might have come across these different types of free radical initiators, but many of them would be kind of new to you. And we will be looking into the structural aspects and how they give rise to the various free radicals for carrying out this free radical polymerization. Okay, so let us move on to our first type of free radical initiator, and that is peroxide and hydroperoxide form. And now this particular um, form of initiators you're pretty aware of, because often whenever you talk about any radical formation, you always talk about compounds such as peroxides or hydroperoxides. Now, are the most common type of initiator. That's what I said just now, that most of the time the peroxides that you're going to see are the one uh, that is peroxides or hydroperoxide base. Now, these type of free radical initiators are usually thermally unstable, and they dissociate readily into radicals at a particular temperature. Now, this doesn't mean that you take the peroxide and it just decomposes into radical, then it would be of no use. Okay, so it's not like that. You require a specific temperature at which this peroxide dissociate into radicals. Not it's usually these peroxides that we are using for free radical polymerization processes, they are stable at room temperature. They only start to decompose only at a very higher or slightly higher temperature. For example, this particular peroxide, you are pretty aware of benzoyl peroxide. This is the structure of the benzoyl peroxides, as you can see here. Now, this peroxide decomposes at only at a temperature of 100 degrees centigrade. So that means at room temperature, they are pretty stable. So when you heat it to 100 degrees centigrade, it undergo a homolysis at this bond to form a benzoyl oxy radical. This is called as benzoyl because this particular part, that is PHCO, is called benzoyl. So benzoyl oxy radical. Okay, so this is how by homolysis this peroxide generate the radicals. Now you might be thinking, what are these reactions mentioned here? Often what happens is that uh, after this radicals is generated in the reaction, they undergo certain side reactions, okay, leading to the consumption of our required reaction. That means these are wastage reaction because it wastes the original radical. Because you can see here, this particular benzoyl oxy radical is kind of um, decomposing into a phenyl radical and a carbon dioxide. And these phenyl radicals further react to neutralize themselves. And this can neutralize via this particular reaction as well. So these 6.2, 6.3, 6.4, these are kind of reactions which are actually wasting your benzoyl oxy radicals. Okay, so now what is the reason why these side reactions is happening is because of the confinement effect of the solvent molecules. Now, what do you mean by the confinement effect of the solvent molecules? See, as the name, as this particular term itself suggests, the solvent is trying to confine these radicals into a like cage, into a cage. So solvent itself form a cage around these radicals. So because of that, what happens? These radicals are kind of trapped inside the solvent cage. So they constantly collide among itself, and therefore, since they are constantly colliding with itself, they are kind of decomposing to neutral species like this diphenyl and these kind of phenyl benzoic ester. Okay, so this side reactions is happening because of the confinement effect of the solvent molecules, or it is also called as the cage effect. Now, another kind of wastage reaction is a kind of induced decomposition. That means the phenyl radical that is generated because of the confinement effect can react with the neutral benzoyl peroxide compound to generate neutral species and thereby generating phenyl benzoyl oxy radical, but still it is one because if you look at the original reaction, when it undergo homolysis, it forms two benzoyl oxy radical. But if this induced reaction happen, what happens? Only one molecule of benzoyl oxy radical is produced. So that reduces the yield of the activated monomer. Okay, so that is why these reactions, that is the 6.2, 6.3, 6.4, and this particular induced decomposition 6.5, are called as wastage reaction because it wastes your free radical initiator. Now, the other examples of these peroxide radical involves this diacetyl peroxide radical, and then this is ditertiary butyl peroxide radical. Now, please read this sentence carefully. It says that the side reactions that are happening, that means these wastage reactions is happening depends on the structure of the peroxide. So stability of the initially formed radical and the reactivity of the monomer. So if your uh, radical, peroxy radical that is generated out of this peroxide is not stable, then it would lead to more of the wastage reaction. However, if your peroxy radical is pretty stable, okay, then it has a lesser chance of it to undergo any kind of um, wastage reaction. Apart from that, if your monomer, that is the vinyl monomer that you are using in this reaction, if it is reactive enough, then it will quickly react with the radical peroxy radical, thereby not allowing that radical enough time to undergo any kind of wastage reaction. So this way you can prevent these wastage reaction to happen. Now, it depends upon the structure of the peroxide. So when we talk about this benzoyl peroxy radical, it is pretty stable because it has a half-life of approximately, in the previous slide, I gave you that it's a half-life of 30 minutes. So it's the wastage reaction that is happening in the peroxide when you use benzoyl peroxide is pretty low. Now, what is responsible for their stability is pretty easy to understand, because you have a conjugation happening here. So you have a pi cloud, and this pi cloud can interact with the pi cloud of the benzene ring, and therefore this benzoyl oxy radical is stabilized in this particular thing by the conjugation with the phenyl pi cloud. Okay. Now, if we consider diacetyl peroxide with the benzoyl radical, here we have conjugation stability is happening, but it's not stabilized by the pi cloud as you see in the case of benzoyl oxy radical. And that is why if you use diacetyl peroxide as a radical initiator, this particular initiator will have a lot of wastage reaction because of its lower stability. Now, when you compare your benzoyl peroxy radical with this ditertiary butyl peroxide, you can see the half-life has increased by a 10 hour. Okay, now that means it is pretty more stable. Now you ask why it is more stable? Because here, when it undergo homolysis, it generate the tertiary butyl peroxy radical. Okay, now this particular radical is very much stabilized by almost 3 threes and 9 hydrogens by hyperconjugation. So that is why, because this particular radical is very stable, because hyperconjugation, it's not just one CH3 stabilizing, it's almost 3 CH3 groups stabilizing via hyperconjugation. So probably that is one reason why this particular radical is more stable, and therefore this particular initiator, if you use in your free radical initiator process, it will lead to minimum wastage during this particular polymerization process. Okay, so the wastage depends upon the structure of the peroxide. Okay. Now, apart from the usual peroxide, you can have hydroperoxide. So that means rather than R here, it can be H. So it is hydroperoxide. Now, hydroperoxide also undergo thermal decomposition, but often they have this 6.7, 6.2 are kind of wastage reaction, because what happens here is induced. Here, what is happening is a induced decomposition. So while the polymer chain is growing, abruptly what happens, this radical reacts with the hydroperoxide, and thereby terminating the increasing chain. So once this is formed, it just quickly decomposes to give you a this kind of a radical, but the chain has been terminated abruptly. So this lead to shortening of the chain length. Okay, our job is to get polymer chains of higher length. Okay, so but this induced decomposition lead to a faster chain termination, and therefore is a a kind of wastage reaction that is happening. So often usage of hydroperoxide is pretty less, but you might have heard about this. There is usage of cumyl hydroperoxide, probably because though we have generation of this hydroxy radical, but this cumyl peroxide radical, this is pretty more stabilized also by the pi cloud and also by hyperconjugation. So probably that's why this particular radical is used for doing the free radical polymerization. Okay, and as we know that a particular temperature is required for carrying out the decomposition of these peroxides, we can carry like benzoyl peroxide usually required a temperature of 100-degree for it to undergo homolysis. But you can make this to happen at even a lower temperature. Okay, for that you use certain promoters like this NN dimethyl uh, aniline, NN dimethyl aniline. If you use it reacts with the radical to generate ultimately this particular cationic radical. Okay, and ultimately it leads to the formation of this benzoyl peroxy radical. Now this might be involved in both cationic polymerization as well as a radical based polymerization, but we are not pretty sure about how this is involved in any kind of free radical polymerization. But this we know that this is the basic initiator that is involved in the free radical polymerization. So uh, this is another way of inducing the reaction at a pretty lower temperature. For this, we use certain promoters like this NN dimethyl aniline, and it undergo the reaction to form our required benzoyl oxy radicals, which is used for the free radical polymerization. Now, a drawback of this particular process is that usually homolysis will generate two molecules of this benzoyl oxy radicals, but when you use these promoters, you only generate one molecule of the radical. Though we have generation of a cationic species here, which can be involved in a cationic type of polymerization. So often it is said that if you use such promoters, it can have both a free radical polymerization and also ionic polymerization happening. But we are not very sure about the exact mechanism, but it is being said that both are possible, like free radical mechanism is also possible and ionic mechanism is also possible. So I hope you understood our first type of free radical initiator that we use, that is the peroxide radical and the hydroperoxide radical. And this is the most commonly used radical for the free radical polymerization. Okay, so we'll discuss more of these radicals in the coming video. Thank you very much for your attention.